This is the first in a series of about 10 webinars that we're going to have on some functional safety, more of a technical view of safety requirements and implementation. This is going to be pretty non-product specific. We're not going to be saying how to wire our light curtains specifically or how to set up our roto scanner specifically. We're going to look at it more of a broad view of safety in general and how it should be implemented the safest and the correct way according to OSHA guidelines and ANSI guidelines so that we can all be safe. So the purpose of this is going to be, like I said, an ongoing webinar focusing on the technical aspects of machine safety to help everybody better understand recognizing what hazards are present and the correct way to safeguard them. Anybody who's been in a plant has seen a machine with light curtains put on it that maybe has not been put on in the correct way. We all know that just because you put a safety device on a machine does not mean that that machine is now safe. So hopefully we can give you the information you need to put it on the correct way, mount it the correct way, and other things of that nature. This first webinar we're going to be going through is just kind of an introduction to safety. We're not going to get too technical in any of the things we're speaking about, but we should give you a couple of the good benefits of why we need a safe environment and some of the quick ways we can check on things. The future webinars we're going to be having are going to be more technical and they'll be a little more specific to individual topics, and towards the end of the webinar here we'll show you a list of some of those topics that are coming up. Something that we're definitely open to is if there are situations that you have come across in the past or something you see rather frequently that you maybe have questions on, feel free to always email me. At the end of the webinar, my email will be on there, as well as Mark Smokowitz, who's our safety product manager. And if you have any recommendations for maybe some training topics that you'd like to see in the future, by all means, let us know, and maybe we'll put that on the list for the future. So this series really is intended for anybody who designs machines, builds machines, modify, install, operate, maintain any type of machine guarding safety devices, anybody who's in sales of these items as well, distributors in particular. It's good to have this information to know when you're quoting out a system what all is really necessary to make it a safe system. As I said before, just throwing a light curtain on something doesn't make it safe. We need to know and look at the whole big picture of what is necessary to make that machine safe. It's also for anybody who's concerned with any type of safety training, anybody who does EH&S at any plant, and you're looking for specific guidelines to kind of help you pick things out. It's also for people like that. So what are the real benefits of us having safety? Well, one of the easiest and best ways to make this visible is money. Everybody wants money. So obviously, when you have a lost time accident or any type of an accident like that, there's always the immediate cost that you see just from the accident, but there's also those hidden costs such as your workman's comp experience multipliers, your insurance premiums. All that's affected by any of your safety issues that you may have. As you see here, we have a couple examples of a couple companies that brought their experience modification rate down and saved themselves $200,000 in 1 year, and another one here showing they saved $82,000 per year for the last 3 years just by bringing their experience modification rate down. So if you look at it in a big picture type of way, National Safety Council estimates a worker with no lost time accident, which would be one of the more minor type accidents, costs about $7,000 on average. So if you want to cover those costs with your profit, for example, a company making a profit margin of 3% versus a $5,000 cost for the accident, that equals $167,000 in extra sales that are needed based on that 3% margin to cover that one accident, and that's only a $5,000 accident. If you have any type of a larger accident, you can see how quickly that can escalate to very large sums of money. So it always makes sense to be preventative in a situation like this and, stop it before any of this stuff ever comes up. OSHA, as you see, estimates that for about every dollar you invest in workplace safety and health, that you see about a $4 to $6 return, and that's kind of exemplified in the slide we saw previously, where you have such a large multiplier effect when you have any type of an accident. So the top 10 benefits we see, besides just monies, we have decreased work-related accident absenteeism. Obviously, if somebody gets hurt, they miss work. That's a burden on the other workers, as well as lost productivity. Decreased workers' compensation costs, as we saw before. Decreased health care costs, again, back to the insurance premiums. Decreased scrap waste, that's kind of one of those hidden type costs. You bring in a new worker who doesn't know what they're doing, maybe they make some bad parts, that's good product you're throwing in the trash. That's another cost. That kind of lends its way back to the efficiency. Increased quality by keeping the same workers and not having to train newer ones. Higher productivity. Better brand image by not having a plant that has lost time accidents all the time obviously makes them look better. The morale obviously goes up. Anytime there's a serious type accident, obviously the morale of the other workers is going to go down. And increased employee retention rates. Employees obviously would like to work in a place where they don't have to worry about any type of injuries. So who is really responsible for the safety? In the end, we all are. The manufacturer is responsible for the design and construction of the machine in a safe manner. The instruction manual, the operator manual, and the maintenance manual all need to reflect those safety devices, how they need to be taken care of, and how they should be implemented correctly. The user is responsible for the overall safety of the machine as they operate it. The maintenance inspection procedures, which need to be done, most plants have that done every shift. The training of these people is also necessary. Layout, installation, testing, startup, again, setup, operation, maintenance, and then the operator must comply with these instructions that have been laid out for them. So in the United States and Canada, North America, the responsibilities and legal implications, most people think, well, isn't the manufacturer of this machine the one who is ultimately responsible for the safety and safeguards on that machine? And really that's not exactly true. In the United States and Canada, once that machine comes into your plant and you sign off on it, the manufacturer is basically out of the loop now. They can't prove that you didn't make any differences to or any changes to that machine once they left. So as long as you signed off saying that it was safe to your specifications, they're pretty much off the hook at this point, and now it's your problem. So anytime you're looking at placing an order for new equipment, it's important to make sure that all of these safeguards are put into place before you accept the machinery. Again, this keeps you covered and puts the onus on them to have this done correctly before they get the machine to you. Again, after the machine has been signed off on, it's now yours, and the manufacturer is pretty much out of the loop. So what are the legal implications of having an unsafe work environment? Well, if there is an accident, there will almost always be an investigation, depending on the severity of the accident, which could result in serious legal consequences if negligence can be proven. So if you're in a company and your management becomes aware that there is an unguarded danger point or generally an unsafe condition on a machine, what's the best thing that you can do? Well, you can call a safety professional, clearly identify the hazard, get a safety solution, and use the hierarchical approach, which we'll see on the next slide. Designing it out, which is the best way to do it. Actually, we'll see that on the next slide. Eliminating this hazard by design is obviously the best way we can go about this. Taking the hazard completely away and making it not even there anymore is the best way we can handle that. The next step, if we can't design it out of the machine, would be to control the access to the exposures by safeguarding. This would be hard guarding, AOPDs, light curtains, roto scans, interlock switches, anything like that that can help us control access to the dangerous point. The next one would be to provide safety measures like awareness barriers, signals, you've all seen the yellow caution tape on the floor, signs, warning of pinch points, things like that. The next would be administrative controls, which would be training, procedures, and personal protective equipment. As you can see by the little arrow we have showing here, we go in order of how effective they actually are. So eliminating it completely out obviously is the best way. PPE and procedures and training, the least effective. So how do we know when we have an unsafe condition? Well, a quick general way to check this on any type of machinery is it needs to be sized that such a person cannot reach, and this is where we use the acronym AUTO, around, under, through, or over. If you can reach around the guarding, under the guarding, through the guarding, or over the guarding, assuming there is guarding, and reach the dangerous point to access the hazard, then we have a hazardous situation and we need safeguards put in place. So how do we find what the right type of protection system is once we do know we have this unsafe condition? Well, the first thing that would be the best way to go around this would be a risk assessment of that application. And that would help us find the necessary safety level we need. We'll go over safety levels in some of these in a future webinar. We'll talk about safety integration levels, performance levels, and safety categories and kind of how they intertwine with each other. So then we find, well, what are the dangerous movements? Is it a spindle? Is it a press coming down? Is it a pinch point on a gear? What can happen during the normal operation of the machine that could expose you to those hazards? And you also need to think of what can occur during the setup and maintenance. This is something that a lot of people kind of look past when they're looking at the safety of a machine. That you think about it, how it's going to work when the machine is running, but you need to also be very cognizant of how this machine is worked on as far as the maintenance. A lot of times there are certain parts of the machine that are disabled or bypassed when you go into these setup and maintenance modes. That needs to be taken care of when you do this risk assessment. It needs to be taken account of. So once we know what our hazard is and where it is, then we have to decide what we're going to do to alleviate that hazard. Well, there's a couple different ways we can go. You've got fences, sheet metal for general reduction of danger by axis. We've all seen, robotic cells with fences completely all around the machine, or I've seen casting cells that are completely enclosed in fencing with interlocked doors, things of that nature. If that doesn't work, then maybe we have to go with some type of an AOPD, which would be a single or multiple beam safety device, light curtain, laser scanner, position switches, safety mats. Then we have to have something that's going to evaluate all of these safety devices, so safety relay, safety controller, or a programmable safety controller. We then have to take into account the reaction of the actuators as contactors, valves, drives. It's not always complete when you put a full safety system onto a machine. That doesn't necessarily always fix the problem. You need to look at how these valves are going to, how they're going to be affected by taking power away from them, basically. So if you have a machine that's got single solenoid valves on it, you remove power, that doesn't necessarily stop motion, that just reverses motion. So a lot of these things need to be taken into account when you're doing a full survey of a machine. So there's really three main types of hazard protection we're going to be dealing with. Point of operation guarding, which is when you have an operator who is using a part, maybe in a small process machine, something like that, where they're going to be getting their hands very near to the danger point. And there's different ways for us to guard that, as well as danger zone guarding, which is where you're trying to protect a person from coming into an area. And then we have access guarding, where we're basically trying to stop anybody from going into there without tripping the thing. So the first would be an example of a point of operation guard. Here we have a small process machine, a little press, light curtains, small resolution on the light curtains, fingertip control. That way anybody gets into this, the machine stops, press stop cycling. A hard guard version of something similar to that would be this. Very small openings, can't get your fingers in far enough to get to the dangerous point. Example of an access guarding would be maybe using a multiple light beam device. Here we see a 2-beam version being used for a perimeter guard, and then we have a 3-beam also being used here as a perimeter guard. Both of these circumstances could also use hard guarding if necessary with interlocked doors. And then we have, well, here's a real-life picture of an access guarding example. We have a 3-beam multiple light beam device on both sides of this guarding access. Operator walks in there, places the part down, walks back out, resets the machine, starts back up. So this is an application where hard guarding probably would not work because you'd have to be opening and shutting the door every time you went to place and remove a part. So we do hard guarding on the sides, and then we do a light barrier where the access point is. Example here of a rotoscan type application where we're doing a danger zone. This is kind of unique, whereas that danger zone is going to be a moving point. We have this big gantry that's moving back and forth on these rails. It's not really possible to hard guard this because it is moving. There's really no place to put any type of a light curtain. So in this type of a situation, we have a rotoscan. You can't really see it great in that picture, but you have a rotoscan there. Scanning for a distance in front of this. I'm assuming there's also one on the back side of this machine. So as the machine moves, the dangerous area to stay out of moves along with it, and if somebody were to walk in front or behind this machine, we'd get a signal to stop the machine safely. So when we move on to more of the technical type topics, these are kind of the go-to standards we're going to be referencing a lot. OSHA, obviously, everybody knows about OSHA. In Canada, we have CSA, which is kind of a guideline more than it is a law. Each province has their own laws, but I think they use CSA pretty much as the baseline that they use to make their standards. And then we also go with the European norms. This is a good one to look at because in the future, most of these safety regulations are all going to be standardized, and they're most likely going to be going towards closer to the European norms than what we do here at OSHA. And we can see that in some future webinars we'll do. You'll see the difference when we do just something simple like a safety distance calculation, how different it turns out to be if we go by ANSI RIA, or if we go by European norms, or if we go by OSHA. They all come out to a different distance. As far as electrical, we have NFPA, we have the ANSI, RIA, CSA. Again, these aren't laws, but these are what most of the laws are based on. So some of the future topics we'll be seeing, identifying hazards, performance requirements. So in this type of a topic, we'll be looking a little bit closer. Again, today was just a brief overview. We'll get more in depth on the future webinars, so we'll talk a little bit more about identifying hazards and how to figure out what the performance requirement is to safeguard that hazard. We'll look at safe distance calculation and the effects that resolution and mounting has on that, depending on hard guarding or light curtains. Your resolution, in other words, the spacing between the beams, how big of a part that plays in your safe distance calculation, as well as the way that you mount them, how high they are off the floor, how tall the actual safe guarded area is. We'll look at specific requirements for muting, blanking, and initiation in regards to light curtains. Putting a light curtain on a machine with muting, blanking, or initiation, there are a lot of certain considerations that need to be made, especially in the mounting and the wiring of these devices to make them conform. We'll look at the pros and cons of hard guarding versus AOPDs or optoelectronic guarding, such as light curtains, laser scanners, multiple light beam devices. Specific considerations for power presses. Power presses have a lot of their own guidelines separate from anything else because it is a different type of machine and it is very dangerous. So we'll look at some of those considerations in future webinars. We'll look at different application areas for light beams versus light curtains. What is a type of an instance where a light curtain would work? When would a multiple beam work? Sometimes there's instances where both will work, and we'll kind of go through that and help you figure out what is the best thing you're going to need for that type of a hazard. EDM and restart functions, we'll go through how those work, why we need them, and how to use them correctly. Look at the differences between Type 2 and Type 4 devices in theory as well as in practice, and what you need to know before you make that type of a decision on what type of a device you need to use. We'll look at e-stop circuits and the proper way to implement an e-stop circuit. We see a lot of e-stop circuits in the field that are not being used correctly. So this is something that's kind of important we need to get down, because the e-stop is not like a light curtain. It's not restricting a dangerous movement. It's not restricting access. This is, in truth, an emergency stop. Everything needs to stop. And then we'll look at some of the common mistakes that we see in the field a lot and ways that we can make sure and avoid those. So those will be some of the future topics that we'll be covering. Again, anything you guys have that is specific and you'd like to see, maybe something you have questions on, something you've seen in the field before, you'd like explained a little better, feel free to email myself or Mark, and if it's something that we think is pretty good, we'll do a webinar on it. I don't know if I introduced myself. I am Chris Halstead. I'm the controls engineer here at Leuze Electronic. With me is Mark. He is the product manager for the safety products. Again, you can email either one of us. There we are. Or call with any safety questions you have. If you have any ideas for future topics, be sure and let us know. Anybody on here who's a distributor or a salesperson, you can be sure and pass this on to any of your customers if you'd like. Again, this is not, we're not pushing products on anybody. We're not going to be discussing our products only. We're just going to be looking at the theory and the practice of safety as far as technical aspects of it, mounting, wiring, safety distances, stuff like that. So it's going to be a lot of good information, very non-specific as far as which products. So anybody you can think of that may be benefit from this, be sure to let them know.